Hello, good evening. Welcome, everybody. Thank you for joining us to our webinar. First of all, I would like to make a test. Please, I would like you to confirm if you're listening to me clearly. Okay, very good, very good. Thank you. Thank you for the message. Well, as I said before, today's webinar, it's going to be about, as you can see here in this slide, the impact of a wall. I'm going to present the model and what are we going to do here. Okay, as you can see in this slide, today we're going to make a modeling process of a block. And as you can read here, the block is going to be impacted to a solid wall or a rigid wall. Okay, as you can see, the block is going to fall and is subjected to the weight. So it is subjected to the acceleration of gravity, and it is going to fall until it reaches and impact into the rigid wall. Okay, the main characteristics of the element that we're going to model is a block. It has a height of 1 inches and have a length of 10 inches. Okay, and basically the model, it's going to start with an initial velocity. Okay, and for matter of time and for matter of computational resources, we're going to model the last instant when the block is going to impact to the wall. And as you can see here, during the time interval, the blocks, when the block impact to the wall, it makes an instant of contact. Okay, so now due to that contact and that impact, a compression wave is generated, and it is represented as a dilatational wave. And in that way, when the object hit the another one object, the wave travel to the point in terms of pressure, in terms of stress. The wave is going to the free end to the object, and then it goes back until reaching the reed wall, and it makes what is the called phenomena of rebounding. So what we're going to do here in Civil Fan is we're going to model that process, that behavior. And as you can see, that process of or that behavior is contains a very high nonlinearities, because we're going to model the contact, the time of impact, okay, and we're going to model the velocities, the normal contact forces, and we're going to model how is the spread of the wave propagation of the stresses due to the impact. For this model, we're going to make a few considerations, and we have two basic cases of a study. Okay, first of all, we're going to make a study where we have the block is in an angle of 0 degrees in respect to the horizontal. So in this model, we're going to evaluate the block cracking behavior and the crushing behavior. As I said, we're going to model the block as a generic material with an initial velocity of 100 inches per second. Okay, and in this case, the object it's going to be rotated with an angle of 2 degrees from the horizontal. We also are going to study the block cracking, the crushing, and the the behavior in terms of velocity, in terms of time of contact, and in terms of the stress spreading into the model. Okay, now we're going to proceed to see the model. Okay, and I'm going to explain the main characteristics and the main modeling process what we took into consideration for evaluating the nonlinear behavior and the wave propagation of the stresses due to impact. Okay, as you can see here, we have a 2D model, okay, where we are making the model with two shell. It's composed with shell elements, and with those shell elements, we are conforming to a structural elements. Okay, as I said before, you know, we first define the geometry. Okay, where we define the points, the lines, and all the tools that we have available for generation of the geometric model. Okay, in the process of model, we define the materials, and in this case, we have the main sections where we get materials and we have cross sectionals. In this case, we have defined a block generic material. Okay, here you can see the main properties, the name, and we get the modulus of elasticity. We've got Poisson modulus, and we have defined additionally we have defined the cracking properties to take into consideration. As you can see in this button, we had to check that the model is going to take into account the nonlinear behavior on cracking. And also, we have defined that we're going to evaluate the crushing of the concrete. Okay, and very important point, we are defining the ultimate strain for this block generic material. Okay, as you can see here, it's going to be 0.0035. Okay, this is the strain. Also, we have here, it's important to notice that, uh, as I said before, we're going to model the last instant of velocity, the last instance of displacement, which is for which is traveling this model, which is block is traveling. Okay, so for our modeling process, we're going, and in our results, we're going to evaluate, you know, the displacement, and we're going to evaluate the time of contact. We're going to evaluate the spread of the wave, or the propagation of the wave of stresses, and how it travels along the member, and how it's developed. Here we can see that in this dialog box we have the properties of the wall. As you can see here, I'm going to show you. And well, all the elements are modeled with 2D solid plane stress in this model. Okay, and as you can see here, we've got a merge tolerance of 0.001, and we have an edge size for the elements of 1 inches. Okay, as you can see here, we've got the tolerance margin, the edge size for the wall, for the rigid wall, and we have defined the algorithm that it's going to take place for making the modeling, and and the evaluating of the results. Okay, it's important to notice that, you know, as we are going to evaluate a contact, an impact, okay, which is, we can say that is that, is a dynamic and an instant dynamic analysis also, and adding that we're evaluating the nonlinearities of materials. We have to model the contact. This is the relation that, that it's going to be placed for the two members. Okay, and as we're modeling that, we're modeling the behavior where the element hit the wall and then it rebounds. Okay, so we have to define a touching contact property. Okay, as you can see in this dialog box, we have different conditions for evaluating the contact. For example, I'm going to open here for showing you the different types of contacts. Okay, we only have to define the element which is going to be contacted, and the host element. And here we have the different types of contact. Depending on the kind of contact that we're defining here, it's going to be the way and the non-linear behavior status for these models. For example, as I said, in this model, we're going to use touching contact because it's an instant hit that we're going to model, and we want that the element makes contact into another element and then it gets separated, and we want the model can capture this behavior. Okay, well, in this point, I would like to show you that for the block generic material, we have to define an equivalent plastic strain stress behavior. Okay, and I will show you, which is the curve. Okay, so taking into account the von Mises stresses, we define the equivalent plastic strain behavior, and this is how the model is going to behave and how we get all the information, for complaining the behavior. Let me check here. Okay, we also have stated an initial condition, okay, and our initial condition, it's going to be the velocity. As you can see here, the velocity in x component, it's going to be 100 inches per second, okay. So this is going to be our initial value problem for this, for making the solution of this model. We also have to define the global solution controls in order for us to capture the nonlinearities of the model. As you can see here, we have to define the integration method, which is generalized. We have to define the step fractions, the total increments. We also have to check the convergence. In this case, we're going to use the F convergence and the contact method. As I said, in this case, we're using segment-to-segment contact method. So by this way, we can capture a high nonlinear behavior between the elements. And well, this is a great feature of Civil FEM because in a few steps we can define and we can evaluate a very complex behavior such as this. Okay, so once we have defined the model, geometry, the mesh controls, and the loads, or in this case, the initial values problems, or initial values, in this case is velocity, we run the model and we're going to see the results. In this case, the first step that we're going to evaluate is the translational velocity. This is the instant of time, okay? This is the velocity in a graph where we can observe the development of the velocity in x direction, and when suddenly we lose that velocity because of the impact into the wall. So first we have to load the results in order to make the proper data for making a table or a graph. Okay, this is done. These are the different results or result steps for the model. And what we're going to do is, we're going to define the axis for the time, that it's going to be the x-axis, and then we are going to select a node. Okay, let me type a name here. I'm going to write x component of velocity. Okay, we have to place a node result. Okay, first let's activate the nodes for you to understand what nodes are we getting here. So we're going to select the node 106 and the node 111. So basically in these 2 points, we're going to make the graphic here. Let me check. Okay, VTX. Well, let's get 106 only. You press the chat button and you can see here the velocity. So what we are watching here, we can see that the model can capture the initial velocity and it is developing in the terms of time, and suddenly it breaks down onto zero. That behavior is representing the moment of the impact. So easily we can see here that in this time the block is coming with an initial velocity, it is constant, and it falls in the moment of the impact into the wall. Okay, so now I would like to show you the displacement. In the same process, we are going to, let me change the name here. We define the node, the type of result, which is nodal. Okay, and let's say we're going to evaluate the node 111. And the component, it's going to be displacement in x direction. Okay, now you can see that there is a trace of the displacement in the time zero, and it start, you know, it start developing linearly until it reaches the impact into the wall. So in this way, you can evaluate and you can prove that your model is it's getting a behavior as you want, because in the time, as you can see here, a little bit less than 0001, it's the time when the block get in contact into the wall. So as I said, we modeled the last instant of time when the object was approaching into the read wall. Okay, now CivilFem has a very powerful tool, which is the capability of evaluating the contact status. Okay, so the contact status is a representation between 0 and 1, and you know, selecting a node, we can we can observe by a graphical representation the exact period of time that a defined node is getting into a real contact, and we can measure, you know, the amount of contact. If we talk about in percentage, we can say that in a period of time the mobile can have 100% of contact, 80% of contact. So here, as I was telling you, in the x-axis we have the time, and the vertical axis we have the contact status. Okay, so you can see that it's starting 0 because in that time the object is traveling. You know, that little distance that I showed you before, the object is traveling that distance, and when it gets impacted into the wall, we get the value of 1 in the terms of the contact status. So logically, that means that the object has impacted. Okay, and we can see that in the rest of the time, the amount of contact is 100%. And you know, for for all those engineers who work, you know, in, uh, in Florida, in Georgia, in any state, you know, for example, in Florida, we have to make the NOA for you know, for any components that we are designing or that we're going to use in our project. And we have to make, you know, we have to develop a test process. Okay, and sometimes this is a powerful tool because we can simulate, for example, a glass impact. We can get all the information of the glass, for example, and you know, we can calibrate our model, and well, we can simulate a missile impact with the glass, and we can evaluate the real behavior because by means of the capabilities of civil FEM, we can we can capture all those nonlinearities that are characteristic of a real behavior. Okay, so this is a very powerful tool, you know, for making missile impact test, for evaluating all kind of elements such as concrete, glass. As I said, you know, it's a very powerful tool. Okay, and now I would like to show you. Let me show you. Let me select these two information and plot again. Okay, okay. Well, here we got the information of the plastic strain. What is representing here when we say about plastic strain? Remember that when we were defining the material parameters, we said that, you know, the ultimate strain for the material it's 0.0035. Okay, this is our level. So we have to note the node 1000 and the node 996. So what we are observing here is, let me show you. I'm going to show you the nodes. I want to show you the nodes. Okay. Okay. You can see here in the top, you can see the node 1000. Okay. And by the, sorry, the element 1000. And by the end around, you can see the element 996. Okay. You got to be present with this. Okay. So what we are defining here is that the node 996, it reaches the maximum strain. Okay, so that means that in that point, the element is crushing. Okay, because as we said, we are reaching that point. Okay, so, but the other node, which is the node 1000, you can see there in the graph that it doesn't reach that level. Okay, so that means that, you know, the spread of the plasticity in the model is not is not is not linear, it's not constant for all the elements. It depends the position of the of the element. In this case, the shell element, which define the particles. Well, this depends on that, and well, we can capture the nonlinear plastic strain using this graph, and we can see which elements or what level of elements are reaching the crushing of the material. It could be concrete. In this case is a general material that we defined. Okay, now I would like to show you, this is a very good tool that we have in Civil Fan. I would like to show you graphically the behavior step by step of the crushing of the element. Okay, so I'm going to load around the step 250. Let me get that point. Let me check. Okay, and we're going to evaluate the plastic strain, the equivalent plastic strain. Okay, as I said before, this is representing the crushing of the element. Okay, so you can see that on that time, just in the contact of the element, you can see how the red zone in that little instant start reaching the plastic strain. That means that the element start crushing in that point. As you can see here in this level, point 0.00349. Okay, this zone first is reaching that. Okay, so I'm going to move step by step. Okay, and you can see how the propagation of the wave it's going to the free end of the element. Okay, and all that zone is reaching the plastic strain. And well, by this way we can see the propagation of this kind of stresses and strains. So now I'm gonna plot a further step. Let's say that let's plot the step around 70, for example, or sorry, 700. Okay, let's go until the last step. So now you can see here how is the propagation of the strain on that zone. Okay, so as you can see here, all the red zone has reached at the end of the step, has reached the maximum strain defined for crushing. Okay, now I would like to show you, okay, that we also can plot, the XY component of displacement. That means that is the angular deformation that is occurring in the moment of the impact. As you can see here, We have zero stress and zero deformation, okay, and in the XY plane. And once we reach the impact, for different nodes, the behavior is different, okay, and we can capture that information based on the non-linearities capabilities of civil fan. Okay, so here we got. I'm gonna show you the information with the model taking into account 2 degrees of rotation. Okay, in the same manner, we can evaluate the component of displacements, in this case for these nodes, and we can plot it. We can plot all the information, okay, and evaluate which node it's getting contact, or the rate of displacement for each of those nodes. And we also can evaluate the status of the contact status for those nodes, and we can see here which of them are getting contact in the same time. Okay, I'm gonna go to the next. Okay, we also can see here that for different nodes, we have the plastic strain, and now as they are not getting into contact in the same time and in the same inclination, we're gonna have different behaviors of the plastic deformations for different nodes. As you can see here in the slide, we can see that in the moment of impact, all the top of the block is crushing against the wall. But the node 101, which is defined here, it is not it is not happening nothing there because it is not getting in contact. Okay, yeah, for all those nodes, we also evaluated the normal stress of contact, and we have that. We can see here that it's pretty different. It's very different the behavior in terms of the position, as I said before. And those complex nonlinearities, we can capture them, by the tools available of civil FEM. We also evaluated the XY component of the stresses, okay, for those nodes. And we could see that, on civil FEM, we have the great capability of capturing all the necessary information that we need in order for us to make forensic analysis, in order to make test analysis. Okay, so basically, this is a very powerful technique that we can use for problems as complex as, maybe evaluating dynamical behavior and wave propagations.